This bell work is just a little bit different than what we saw in the last unit because on this one we do have some combining of like terms that we need on this one, particularly with this negative 1y. Okay, so we got this negative 6y's and negative 1y's. How many y's would that be? Be negative 7y's. Okay, and I can still drop this positive 4 because there were no other like terms to combine it with over here. It's just a constant. And then this still equals the negative 31. Okay, from this point, it's just a two-step equation. Meaning the first thing I'm going to do is make a 0. And to do that, I'm talking about that plus 4. I'm going to make it a 0 by subtracting 4 from both sides. Okay, so that will zero that out. I'll still drop my negative 7y's here, but now it equals negative 31 minus 4, which is negative 35. Last thing I need is for the final answer to show as 1y instead of negative 7y's. So how to make a negative 7 to 1? Just divide it by itself, negative 7. Okay, so divided by negative 7, and I get 1y equals, now it's positive 5. Okay, now if we did this right, then this should work. So I'd say negative 6 times 5 is negative 30, plus 4 is negative 31. Remember we had this one right here. That's negative 30 rather, sorry. Negative 30 plus 4, that'd be negative 26, and then minus, well, it would be really minus 5. That would make that negative 31. So it does check off that 1y equals 5. This would actually be the solution here, okay? And we did check. Here's our first objective for this new unit. I can use principles of equality to solve inequalities. Take a minute, take 30 seconds to copy that down, please. So the difference between this unit and the last one is there's only one difference that we're going to be seeing right now, and we won't even see it today. So if you feel comfortable using principles of equality to solve equalities, like we did in the entire last unit, then this unit should go pretty well for you, especially this section. There is one exception, but we're going to talk about that next time, I believe. So what is an inequality? It's a math sentence that compares quantities, just like an equal sign does, okay? Because we could say, look, here's an equal sign. It compares values. So you could say, well, 5 compared to 4, right? And you'd say, well, that's just a false statement. It's correct that this is a false statement, but it still is a comparison. We just say that this one here is just false. That's it, okay? And we saw as well that it's possible to have true equal statements, right? You just say maybe 6 does equal 6, and that would be true. You know what I'm saying? So it's still a comparison of values. You have to check for truthfulness or falsefulness. It's just now we're using new types of symbols. We won't be seeing equal signs by themselves between the sentences. So really, this is the type of inequalities we can expect to see, these types of symbols. We see this one right here. I remember that it's less than because it kind of looks like an L for less than, right here. The next one is greater than, and to me it kind of looks like this part of the G. You just put a little swoop there, right? So that's how I remember. Some people just say, memorize a less than, and then I keep it that way. Now, something new for us is where we got this symbol underneath it. Okay, this starts as a less than symbol, but then it also has an equal to symbol with it, but it's only part of the equal sign, okay? And as long as you can remember that, then you know that we're looking at less than or equal to. You'll notice here that the statement is an or statement. That's on purpose because you can't actually have something that's less than and equal to something else. Which means that for this particular scenario, for either one of these, by the way, only one of the two statements needs to be true, okay? So like this one, less than or equal to, if you see a value that's less than, that can be true. If you see one that's equal to, that can also be true. And so this one, where it's got the greater than symbol, but the line underneath it, that's a greater than or equal to symbol. So if it's greater than, that's good. If it's equal to, that also would make the statement true. Now there's different ways to express these with words. We're not really going to be looking at those necessarily, but just less than, greater than, less than or equal to, or greater than or equal to. So those are kind of new for us. Let's look at this scenario right here. Okay, so for these values, we're going to determine if the statement is true or false, this inequality. So to start out here, it says k is 5, right? So I say, let's replace the k with 5, and then I'm going to check for truthfulness, right? So it's 7 times 5 should be greater than 35 right here, but we're checking for truthfulness. Well, last time I checked, 7 times 5 is 35, and the statement now shows 35 is greater than 35. Again, a question mark? No, this is false. Okay, so we can see here that 5, if you replace the k with 5 here, you end up with a false statement. All right, yeah, let's do check that next one, right? So we're going to say now z equals 7, so I replace the z here with 7, I guess. In fact, we may even change it to something else here. But 7 times 7, is that greater than or equal to 35? And yeah, we can see that 7 times 7 is 49. Now 49, and yeah, there's a question mark over the inequality there, but 49 is greater than or equal to 35. Now remember, even though 49 is not equal to 35, this one is still true because 49 actually is greater. It satisfies this greater part of it, so that makes this true. Okay, now let's go back and look at this one. Let's say that I go in here and I take the 7 and I replace it. Let's just replace it with 5 and see what happens, okay? So I say, well, let's replace this with 5. Then we'll see what happens. So I'm going to replace my 7. So this is kind of like a new problem for us. Okay, and we'll see if this is true or false. But 7 times 5, that would be 35. And now we see that it's not the greater than part that makes this true. It's the equal part that makes this true, but it is still, in fact, true. Okay? So I guess we kind of checked that one twice. But that's how you can tell if values as letters make these statements true. But what you notice from this also, that just from the second problem, we had 2 values that made these that made this inequality true. That's because for these types of inequalities, generally speaking, there usually is an infinite number of solutions. Now, the problem with us in the past is we've seen answers come out as just something like, I don't know, x equals 11, maybe even it's negative 11, okay? Maybe it's a fraction or decimal, doesn't matter, but we saw that all of our equations only had one answer. Now we're saying that there's an infinite number of answers or an infinite number of solutions. This is where it comes, it falls upon us to be able to show that there's an infinite number of solutions and which ones make it true. Okay, because just like this one right here, this value of 5 made it false. So simultaneously, while there's usually an infinite number of solutions, we can also say there is an infinite number of non-solutions. Okay? So when we write out our answers with inequalities, we're showing the infinite number of solutions, which also indirectly tells us which values would not be solutions. We're not going to be using equal signs in our comparisons anymore. It's important to understand how this one reads right here. This is saying that 35 is greater than 35. We can put a question mark after that. And so this takes some thought, especially while we get used to this, while we're checking for truthfulness or falsefulness. 35 is greater than 35? No, I've never seen that be true. It's the same exact value. So you have to actually read these, and then in your mind, again, you may have to ask yourself this several times, is that actually true or not? No, this one right here is not true. Okay, and then this next one, just the way that I have it when I replace z with 5, is like saying, is 35 greater than or equal to 35? Well, now we know that it's not greater than, but it definitely is equal to 35, which again, that makes that a true statement. That's why we get a yes out of that one, or true. All right, so here's our principles of equality: addition, subtraction, multiplication, and division. And going back, we know that when we see addition and subtraction, these two right here, the purpose of these both is to make zeros. okay? Now for us, we're usually just making a 0, but do understand that you can make many zeros if you really needed to, okay? Now I'm pointing this out because some of you forgot this while taking the test, or just haven't really paid attention, so didn't know what the crap you're doing, okay? There's an objective when using these principles of equality. We could just use them randomly, but then that doesn't really help us, okay? Then we also have multiplication and division. This is to make specifically the coefficient a 1, okay? Mr. Sal, I don't know what the crap a coefficient is. Well, we've gone over it several times. A coefficient is just the number being multiplied by the letter. Okay, so if we looked at an example of a coefficient right here, like, if I can zoom in here, this would be like 2x. The coefficient is just 2. Okay, but we wouldn't want 2x's. We would want 1x's. We pretty much did this, use these, two of these principles of equality on the bell work, okay? So if you look at the bell work, you can see that we made a 0, then we made a 1. Now, again, with inequalities, there is one extra rule, but we shouldn't see that today. All right, so remember solving equations, and we haven't even seen these first 2 steps yet. We have done distribution, and we have combined like terms, but we haven't seen that they were necessary when we were solving our equations. All we were doing was using principles of equality to isolate the variable, and really what that means is to make a 0. Okay, and then when we say we're going to divide by the coefficient, sometimes we did see that there was some multiplication there. That was to make a 1. Okay, so we made a 0, we made a 1, and that was solving our equations. Now what we have is there's one extra rule. We're not going to see this, but if the coefficient is negative, meaning that, and again, I'm getting a little ahead of myself here, but if you ever multiply or divide both sides by a negative, then you flip the inequality, okay? Now again, we're not going to see this today, but I do want you to know that it is coming. We should see this during the next lesson, but you see everything else remains the same. You got distribution, combining like terms, which we shouldn't see, but principles of equality to isolate the variable. We're going to see that. Again, that's to make zeros, and then divide by the coefficient, that's to make a 1. I guess on the bell work, we did see a little combining like terms, but we saw also that it wasn't too difficult, it's just a little extra work. So here's this one, right? Negative 14 plus x equals negative 62. Now remember, the objective right now is to get the x by itself. So I am using a principle of equality here. I'm isolating the x, meaning I just want it by itself. Or in other words, it's like I'm going to take this, by the way, it's 1x. I'm going to take this 1x and I would really like to just drop it, okay? And I don't want anything added or subtracted to it, like this negative 14. I don't want that garbage, okay? So how do I get rid of it? That's where we make it a 0. And again, we have seen that we saw that on the bell work. So I would add 14 there, but if I do it to one side, I would also have to do it to the other side, okay? So in the calculator, negative 62 plus 14, enter, and I get negative 48 on the right side. Now remember, this red line right here pretty much just dropped the inequality for us. And addition and subtraction principles of equality will never flip the inequality, okay? Now, right now the coefficient of x is a 1, that's great news, because since it is a 1, this means that this is pretty much complete right here. Okay, now this is the solution. Really, I should put solutions, because we're communicating right now that, and I guess this is really how this would read, any value for x, well, any value greater than negative 48 or 48, negative 48, would make the inequality true, okay? So think about this. Any value greater than negative 48 or negative 48 would make the inequality true. So what are some values that could make this true? Again, we are also saying that there are an infinite number of solutions here. It's just, we're showing this where it ends, okay? So this is saying, if you replace x with negative 48, that's where it begins to be true. If you go less than negative 48, then suddenly your original inequality would be false. But any value greater than negative 48, let's say like 0. 0 is greater than negative 48. If you replace 0 in here as your x, you're going to get a true statement. Or anything bigger than negative 48. All right, solve this inequality, no problem. Okay, and then we'll get to the second question, would negative 15 be a solution to the inequality? So here we got to actually check this, but let's start with x plus 7 right there. Now remember, right here, if I can just take this x, and if I can just drop it so that it's by itself, and yes, right now it is a 1x. Coefficient of x here is 1, but I don't want that plus 7 there. I want to make that a 0 by subtracting 7. Just if I do it to one side, I'm going to have to do it to the other side, okay? So 33 minus 7, there's 26. So right now, and again, this line right here just drops that greater than symbol down. So right now we're saying anything greater than 26 would be true. Okay? So any value greater than 26, like, I don't know, 27 or 28 or 29, etc. Those values would make the original inequality true, right? All right, so what are some values greater than 26? Like 27, 28, 29. Let's take this to a large extreme, like 500 million, okay? If I said I'm going to replace x with 500 million, would it still be true? Sure it would. And while that is an extreme example, that's okay. We can deal in extremes right now because mathematically speaking, 500 million really is not that much. All right, now if it was money, you might say, well, that's kind of a lot of money unless, you work in the government. So on this one, would negative 15 be a solution to the inequality? Well, we see if you replace x, just looking at even at this x right here, negative 15 plus 7, that gives you negative 8. Negative 8 is not greater than 33, which means would negative 15 be a solution? No, I guess I'll just say no. If you wanted to say false because it just feels right, I don't really care. All right? But again, this inequality is actually communicating that there are an infinite number of solutions. It's just, it switches at 26. Now 26, of course, would be false in the original because it would be equal. And since there's not an equal part of this inequality, 26 still makes it false. But that's where it begins to be equal, and then it switches over to being true once you make values bigger than 26. So here's this one. We got 4. That's 4 times x, you guys. 4 times x is greater than or equal to negative 16. You guys try this one out, and we'll go over, okay? 1 minute. All right, let's go and get started on this one. If you're still working, do finish up. But right here we got 4x is greater than or equal to negative 16. Remember, we want 1x's, not 4x's. So how do we make that 4 1? Well, to do that, we're going to take that 4 and divide it by itself. 4 divided by 4 is 1. It's just, if I do it to one side, I'm going to have to do it the other side, okay? So 4 divided by 4 is 1, and that's where this 1x comes from. And yeah, we're going to bring down our inequality. It's still greater than or equal to, but negative 16 divided by 4 is negative 4. I think there was a problem like this on the last test that we took, and several of you missed this because you forgot the negative. You got to remember those negatives if you want full credit, right? Now again, this is our final inequality, but it's saying that x, if you make a value of x that's greater than negative 4, you're going to get a true statement. But it's also saying, since we got the equal part of the inequality, if you make x actually negative 4, it would remain true. Okay, so indirectly, we say anything less than negative 4 would make this a false statement. You could think of values that are less than negative 4. Like negative 5, for example. 4 times negative 5 is negative 20. Yeah, that's not greater than or equal to negative 16. That would make it false. So the moment that you hit x is negative 4 or anything greater, you get a true statement in the original inequality. But again, this has an infinite number of solutions. And since we don't want to have to actually write out all those infinite solutions, is a good way to write it out. Now, along those lines too, there is a different way to show that all the solutions to the inequalities, but right now we're just focused on writing the inequalities that would make the original inequality true. All right, we got the inequality, then we got, is 0 a solution to this inequality? We're going to check. Okay, let's go and get started here. We got x divided by 14 is less than -2. And I think this is the first time we've seen a less than symbol. That's okay. Well, what I do not want is this divide by 14. Remember those fraction lines are actually divide symbols like this. What I really want in the end here is 1x, not x divided by 14. So how do I make divide by 14 a 1? Just multiply it by 14. So times by 14, but if you do it to one side, you're going to have to do it the other side, okay? So again, that's going to bring down our inequality. It's still less than. All right, Mr. Sal, that's fancy, but how do you get a 1x out of that? How do you make this coefficient of 1 from divided by 14? Because 14, this is really 14 divided by 14, which makes that the 1 right there. Now, while I've crossed this out, I think I've said this several times before, but some of you are mistaking me for just canceling these out. This does not mean cancel out. This means 1. It's just a slanted 1 right there, okay? Now on the right side, I got -2 times 14, which is -28. So again, what does this mean in context? This means that if you replace the x in the original inequality with anything less than -28, you get a true statement. Now, this also means that if you replace x with -28 in the original inequality, it would make the statement false, okay? And you could even check that, right? Oh, sorry, I forgot my close parentheses there. But -28 divided by 14, that is -2, and -2 is not actually less than -2. It's equal to -2, but not less than, which is why that would make that false. But anything less than -28 would become, it would make this original inequality true. So what about 0? Is 0 a solution to this inequality? Well, is 0 less than -28? That's really what the question that we would ask right here. Is 0 less than, -28 rather? And the answer is no, it is not less than 28. It's greater than -28, okay? Because it's a -28, not a positive 28. Let's go back, because we get that question, right? What do you mean that's 14 divided by 14? Let's break this down. Let's go back to the original. It's x over 14. So by multiplying that by 14 right here, it's really 14 over 1. And if we go back to the fractions unit, it's like saying this 14 and 14 divided by 14 is 1, and this 14 divided by 14 is 1. Then you could say, well, 1 times x is x, and 1 times 1 is 1. So it's really x over 1, which I just show as 1x. I didn't want to have to show all these steps, because not only is it fraction multiplication, which people hate, but if you can just understand that when you divide by 14, multiplying by 14 gives you 1, yeah, that's a principle of equality that we can use to force that coefficient to be 1. That works too. So here we go. Now we see what would be a two-step equation, but it's an inequality. That's it. We'll get to the second question, but let's solve this first just to see what happens. Okay. So I'm going to start. Remember, first things first is we would want to drop this 3x so that it's by itself, right? We don't want anything added or subtracted to it, except maybe adding or subtracting 0. But we don't want to show that. Now this reads as this -9, which makes this value -9. How do you make a -9 a 0? Well, I'm just going to add 9. -9 plus 9 is 0. It's just if I plus 9 in red there on one side of the inequality, I got to do it the other side, okay? So now I got -3 plus 9, which is now +6. And remember, this line brings down the inequality for us. So this now reads that 6 is less than or equal to 3x's, but I don't want 3x's, I want 1x's. So again, how do you make a 3 a 1? Well, just divide it by 3. If you do it to one side, you're going to have to do it the other side. 3 divided by 3 is 1. And again, this still brings down the inequality for us. Less than or equal to, but 6 divided by 3 is 2, okay? Now, some students struggle with this one because they say, well, the x is on the right side of the inequality. That's okay. You could actually rewrite this if you wanted to with the x or the 1x on the left. Okay, so you could say, well, this is 1x. And remember, we are comparing this with 2 in this inequality right here. Is just notice that this inequality is eating the 1x right there. So if you flip this, you need to make sure that it's still eating the same value, in this case, 1x. These two statements, these two inequalities that I've written, mean exactly the same thing. They're just shown in different ways. But again, what does this really mean? This means that if you, or I'll rephrase that, any value greater than or equal to 2 will make the original inequality a true statement. Okay, and what values are greater than 2? I mean, 2 would work, right? But what value is greater than 2? 10, 15, 200 billion trillion, a gazillion, whatever. I don't know if those are actual formal names, but I also don't care. Okay, so is negative 9 a solution to the inequality? Again, this, if we make this comparison right there, we're really asking, is negative 9 greater than or equal to 2? And the answer to that one, well, we should know, is no. It is definitely not greater than or equal to. I'm comparing it with this inequality, although you could take this negative 9, replace this x, and see if you get a true statement. But this one, if you replace the x with negative 9, you'd get something very, very, very false. Now, strangely enough, some students did better on these two-step type equations where we use two principles of equality to solve equations on the test anyways than they did on the one-steppers. I don't really understand that, but maybe it's just like a negative or something was missed. I don't know. In any case, this one, we're going to require 2 steps on this one, okay? So for this one right here, yeah, and again, you could bring the inequality down first if you'd like. It's just, I don't want this minus 9 right there, so I'm going to make it a 0 by adding 9 to both sides. I think we did that already, but that's going to make that 0, which means I can drop my x fifths, x over 5 like this. And then negative 7 plus 9 would be positive 2, okay? Now, I don't want x divided by 5, and it's still going to bring the inequality down, but the x divided by 5, how to make that a 1? Well, just multiply both sides by 5, okay? Because 5 divided by 5 is 1, which leaves me with just 1x, and then 2 times 5 there is 10. So in other words, x could be 10, that would make this a true statement, but if you replaced x with anything greater than 10, that would also make the original inequality true. So again, this is not just a solution, it's many, many solutions rolled up into one short statement. Now we'll come full circle back to the objective. I can use principles of equality to solve inequalities. And we did see all 4 principles of equality. We said addition, subtraction, multiplication, and division, or sometimes 2 of them at a time, okay?